In this second part of my lecture, I want to show how ideas and methodologies from machine learning can be used efficiently to design MPC controllers. Machine learning has very good mathematical foundations from artificial intelligence, statistics, and optimization, and most importantly, works very well in practice in a very wide variety of different application domains. And another reason why machine learning it got very popular in recent years is the availability of very good software tools, and in particular in the open source domain, for example, in Python, I mentioned here scikit-learn, TensorFlow, and Keras, and PyTorch, and JAX, and also in Julia. Let's look how we can get prediction models for control. Well, typically in designing control-oriented models, you have two approaches. One is black box modeling. You take data, you run experiments, collect data, and then fit a model by choosing a model class, for example, a deep neural network, and then train the network parameters to get a mathematical relation between input data and output data. Okay. A different approach used more traditionally is physics-based modeling. So you know the process, you know the physics underlying the process. So you could use those physical principles to create models that explain the input-output relations. Now, what is the advantage of physics-based modeling is that the model class that you're considering, it's a lot more structured. The number of parameters you have to tune is smaller compared to the full set of weights and bias terms you have, for example, in a neural network. And it is based on a lot of insight. So you could think that a lot of smart people during the years have developed models, good models for the phenomena that you want to model. So usually a combination of the two is actually the best approach. So you could use a physics-based model to model the part of the model that you know well and that are simple enough, and then use black box modeling for other parts of the process that you don't know how to model, or you don't want to model because the model will be too complex. So what is really the best model to use? Well, let me cite this saying by George Box: all models are wrong, but some are useful. So you don't expect to model the real process very accurately, so you know in advance that the model will not be perfect, but as long as it's useful enough for control design, and in particular for making predictions in the context of MPC, that would be fine. So let me start mentioning neural networks for identifying nonlinear models for control. This is not a new topic at all. I mentioned here some literature from the 90s. There is this nice book, for example, from 96 that summarize a lot of ideas for using neural networks for nonlinear system identification. And this can be used in two ways, either to get nonlinear autoregressive models where you map past outputs and past inputs to the current output. So you model the difference equation by fitting this function by feedforward neural network, or you could fit state space model. So if you have state data available, you could directly fit the state update function and the output function. If you don't have states available, there are also techniques for building state space model from data using neural network. I mentioned here a paper by Prasad and Beckett, where basically the state is defined as one of the inner layers of the network. Or you could fit, in case of MPC problem construction, you could fit the entire prediction as a model. So rather than modeling YT as a function of past inputs and outputs, if you use this model for prediction, as you predict in the future, these equations concatenate with each other. So the nonlinearity gets propagated through the prediction horizon, and getting the Jacobians gets more complicated. And actually the problem becomes very nonlinear. Now, as an alternative, and this is what we have explored in this paper here recently, is to say, let's try to feed directly the whole predicted output as a nonlinear function of the current state and of the inputs that we want to optimize with MPC. Of course, we exploit causality, so the output at time t plus k will depend at most from the input on the inputs between t and t plus k minus 1 if we have strict causality. Or you could use recurrent neural networks, and this we will see next. Let me mention another technique that we have been developing recently, which is based on the use of autoencoders for getting state space model. What is an autoencoder? In very simple word, the autoencoder is a function, usually a neural network, with a hourglass structure. So there is a thin inner layer, and it is trained to map the input to the same input. So this was proposed for image analysis. You're trying to reproduce the same image on the output. And why do you want to do this? Because in the inner layer, you have a compression of the image. So it's a way of reducing the complexity, so the dimension of the input vector in a smaller number of variables. That it's a good encoding, because from these encoded variables, say 30 variables only that you have encoded out of, say, 2,000 or tens of thousands, these variables are enough to reconstruct with a decoder the original image. So together with Daniele Masti, we thought of applying this to generate state space models. So here our image, in quotes, is past outputs and inputs. What we want to reconstruct is the same thing on the other side. Actually, we are not interested in reconstructing the past inputs, so we are interested in reconstructing the past outputs. So we build this structure with a neural network structure with a thin layer, where the thin layer is the state vector that we want to generate. And then we make a copy of this same structure that we feed with the data ik, which is the collection of the data between k and k minus na plus 1 for the output, k and k minus nb plus 1 for the input, while the previous layer is excited with the previous value of the same information vector. So why doing this? Because then you have xk and xk plus 1, and so you can also introduce a new function f to map the state together with the input uk to the next state. And what you do is to train the entire combination. So a copy, this will be a network with the same parameters. So you have a set of parameters for the autoencoder and a set of parameters for the state update function that you train from an input-output data set to build a state space model from data. You could also give some more structure to this. For example, if you introduce a quasi-LPV structure, you could model the state update function as a matrix which depends on x and u times xk and y and 1. So this is an affine function of the state and a linear function of the input, and as well you have a linear function of the output once you fix xk uk. So the idea is that in MPC you can fix xk uk to the nominal values, and this will become a linear prediction model that you can use to construct MPC optimization problem. And this matrix is A, C, and B. Each entry of this matrix can be a feedforward, a simple feedforward neural network, for example. So let's now go a bit deeper in the way we formulate neural networks for control design, and we train them. So let's start with the feedforward neural network model, where this is a typical structure. We have a set of inner layers. Each layer is propagated by an affine function, so you have a set of weights multiplying the values of the inputs to that layer plus constant term. These are training parameters. And then it's followed by an activation function. You take this linear combination and then pass it through a nonlinear, it's called activation function. And then you generate the value for the next layer. So if you do this, you can have just one layer that will be a shallow network, or multiple layers that will be a deep network, and then in the end you have the output, which is either just a linear combination, so it's just equal to VL, or it's a further output function that is applied on the last layer. So what is a training problem for this type of structure, model structure? You have a data set of samples. Okay, so let's say you have n samples, input output samples. What you want to minimize is a sum of losses between yk, what you have in the data set, and what you predict by the model, as a function of theta, where theta collects all the parameters that you have introduced. So in this case would be all the A, I, B, I matrices that you have for the weights and the bias terms in the network. And this loss could be, for example, just the squared error in case of regression problems, or could be other functions in case of classifications. We'll see later. And you often introduce also a regularization term, for example, a penalty on the squared Euclidean norm of the parameter vector for two reasons: to make the problem easier to solve, but also to avoid overfitting the training data, and therefore have a model that badly generalizes when it is applied on new data, on new test data. Now, this problem, because of the activation functions, this problem is a non-convex problem. Could be also non-convex because you're using non-convex loss functions here. It doesn't have constraints unless you consider the model equations as equality constraints, but you could substitute them and remove all the equality constraints. And it can be solved by different optimization methods. Mostly used are stochastic gradient descent methods, especially when you have a large number of data and also a large number of features in X. Those are not very, as I will show later, those are not very good methods in terms of convergence, but they can handle large data sets more easily than other methods like Newton's method, or more used quasi-Newton methods like LBF, GS, or Gauss-Newton methods, or Levenberg-Marquardt methods. And it can be also solved by extended Kalman filtering. So let me show how you can train a feed-forward neural network using extended Kalman filtering. So the idea is not new. Actually, you can find papers in the late 80s, early 90s that show this idea of treating the parameter vector theta as if it were a state with a constant dynamics. Theta k plus 1 equals theta k plus some noise, eta k, that is introduced for Kalman filter design. And therefore, you can design a Kalman filter for this type of dynamics, where the measured output is the output of the function, and the hidden state is theta, is the vector of parameters you want to estimate. So if you use extended Kalman filtering to estimate theta online from a streaming data set of inputs xk and output yk, you can use extended Kalman filtering for online estimation. In this case, the speed of convergence of the Kalman filter depends on the covariance matrices you use for the input noise and for the measurement noise. So in general, the ratio between the variance of the input noise eta and the measurement noise zeta is related to the learning rate. You can show that the initial covariance matrix of the Kalman filter is related to the quadratic regularization term that you have on theta, and this type of approach is also implemented in this deep learning library I was mentioning before, and it can be generalized to arbitrary convex loss functions and regularization terms. This is a recent work I did where I considered more general model, recurrent neural network model, the same ideas apply also to feed-forward models where you only have basically the output equation, but let's consider a more general model where you also have not only parameters you want to estimate with the Kalman filter, but also hidden states that you want to estimate. So let's consider this model where the state equation is a feed-forward neural network which takes xk, uk as an input and is parameterized by a certain set theta x of weights. And the output equation is also another feed-forward neural network with some other parameters, theta y. So what is the training problem? The training problem is to fit measured outputs to predicted output. So how to predict the output? You propagate the model. So you have a loss penalizing the difference between yk and the predicted y, and the states of the model are propagated through the state update equation, and you have a loss on the initial state and the vectors theta x, theta y of parameters. So here the main issue is that not only theta x, theta y are unknowns, but also the states and the whole sequence of states are unknown. They are hidden states and they are variables of the problem that we need to solve for. So how to train recurrent neural networks online? So the idea is to use the extended Kalman filtering approach I was mentioning before. So you have the update of the states through the model, which depends on the vector theta x of parameters. You treat theta x, theta y as constant states, and then you have the output equation. So if you design an extended Kalman filter based on this model, then you can estimate online both the parameters of the model and the states of the model. You can actually use this approach also offline. So start with, say, with random values for theta and run offline the Kalman filter on the training data set you've got from experiments to train the parameter value theta. You can run the Kalman filter multiple times on the same data set, so multiple epochs, to refine the value of theta x and theta y. And then you can use these parameters as initial guesses when you are online to keep refining the model if you want to adapt the model online. And one good thing about this approach is that it can handle quite general loss functions. If they are smooth and strictly convex, you can make quadratic approximations of this function and use them in the extended Kalman filter to minimize those losses. And it can also handle convex non-smooth losses. For example, I've been showing that L1 penalties that you introduce to try to sparsify the model, so try to make some of the parameters equal to 0, depending on how large is the penalty lambda you introduce. You can show that this can be handled by the extended Kalman filter, and actually it turns out that the measurement update of the Kalman filter has an additional term, which is lambda times the state error covariance matrix P times the sign of a vector which contains the sign of the parameters of the model. This is shown in this paper I was mentioning before here. And let me show an example of how this approach works on a data set that I've taken from the system identification toolbox for MATLAB. This contains about 3,500 data of a magnetorheological fluid damper system. I've used 2,000 data for training and the rest for testing the model. And I've considered a recurrent neural network model with 4 hidden states and shallow state update and output function, each one containing 6 neurons, so very small neural networks for the state update and output function, and leaky ReLU activation functions at each node of the network. And what you see here is a comparison of how the mean square error reduces as a function of the number of epochs, so the number of times you process the entire data set. And I've compared this to standard gradient descent method, AMSGRAD applied on the same data set. As you can see, the convergence it's a lot faster in terms of epochs. And of course, each epoch in the extended Kalman filtering approach needs to run more complex operations than gradient descent. On the other hand, if you look at training time, so if you look at the flops you make, then still the extended Kalman filtering approach, it's faster in getting quickly a good model. And actually, even at some point you stop the training, you often end up having a much better quality model than what you can get with gradient descent. And let me show a comparison of what you get with the extended Kalman filtering and AIMS-GRAD. That's actually what you care, how the model will generalize on test data. So let's consider the remaining about 1500 data, and let's test the model on this data. In the system identification toolbox, it was trained a neural network autoregressive model. You get about 88 normalized root mean square error on training data, and a good one, 85 on the test data. With the recurrent neural network model obtained by gradient descent, you get lower values, and you get quite better values with the extended Kalman filtering approach that I have just described. So it's a good method for training simple model. The drawback of the method is that you have to propagate the covariance matrix of the system. So if you have a lot of states, and in particular a lot of training parameters, so a lot of weights and bias term in the network, then this matrix will be larger. What I've noticed is that it's not much the linear algebra you make to update the extended Kalman filter equation, but is the operations that you make to evaluate the Jacobians. But of course, this depends on also on the implementation that you make. And if you introduce a loss in the problem as an L1 penalty on the parameters, you could run the extended Kalman filter with different values of lambda, and you get what you would expect. So the normalized root mean square error gets lower and lower as you increase lambda, because you decrease the emphasis on fitting the output data vector, both on training and also on test data. And on the other hand, what you see is that the percentage of zeros in the model grows, as you would expect, because of the L1 regularization term you have introduced. And here at some point, the penalty is very large, so the Kalman filter starts not behaving well, so it starts losing convergence properties. Okay, so here you could say, okay, I'm okay, say up to say lambda equal 1, I still get a good model, but I get a lot of zeros, which simplifies the model, because then the model equations will be simpler in the sense that they will contain a lot of zeros. So if you take into account the sparsity of the model while constructing the model, you get a lot of advantage. First of all, you will have to evaluate simpler Jacobians, and in evaluating the Jacobians and in propagating the Jacobian matrices to construct the optimization problem, you can keep into account the sparsity so that you have zeros in the A, B, and C matrices. And let me show how this approach would work in case you want to reconstruct a recurrent neural network model of a system that has binary outputs. So this is a kind of a special case of a hybrid system where the output is binary, is either 0 or 1. And in this case, I've considered simple linear dynamics for the state updates, which I assume I don't know at all. So what I can only measure is the input signal I provide to the system and the output, whether it's 0 or 1. So you can train a model which has a linear state space model, so there is no activation function in the state update equation, and you have a sigmoidal output function to generate an output signal which is between 0 and 1. And as a training loss, you can consider the standard cross entropy loss, where this is a modified version of it. I have introduced some positive epsilon so that the quadratic approximation of the loss is well defined. And if you run the approach with different values of the noise signal that enters the state update and the output equation, you could see the behavior of the algorithm. So on training data, you get pretty good reconstruction both on training and on test data. And as you can expect, if you increase the noise level, the training gets worse, but still the algorithm, the extended Kalman filtering algorithm, is able to reconstruct a decent model out of this noisy data set. Now let me show another approach that I have introduced in another paper recently, which is an approach to train recurrent neural networks for modeling the dynamics of nonlinear systems using sequential least squares. So let's look again at the training problem that we have formulated before. So with the loss and the regularization and the state and output equations. Now you can look at this as if it were an optimal control problem, where the network parameters and the initial state are the manipulated variables that you want to optimize. Y hat, the output of the model, is the output of the process you want to optimally control, and yk, the measured output, is the reference signal. And consistently, you can consider the regularization term as an input penalty, and the loss, for example, the square difference between yk and y hat k, as the output penalty. And you have a prediction horizon of n steps, the number of samples, and a control horizon equal to 1, meaning you only have 1 degree of freedom, theta x, theta y, and x0, that you use for the entire prediction. Now, if we look at this problem as an optimal control problem, we can use basically the ideas that we've seen before for nonlinear MPC. So we can linearize the model, okay, and explain the relations between delta xk, which is the difference between xk and the nominal xk that we have obtained starting from a given x0, theta x, theta y. So how these deviations from the current guess for the state and parameters evolves, and the corresponding output evolves if we perturb the initial state and we perturb the vector theta of parameters. And so with this linearized model, and by taking second order Taylor expansions of the loss function and of the regularization term, you can formulate an approximation of this problem by means of least squares, and then run this process sequentially, as we've seen before for nonlinear MPC, by also doing a line search to make sure that your total loss decreases from one least squares iteration to the next. And here you see how the method works on the same data set that we have considered before, the fluid damper system. You see here the blue line is how the mean square error decreases as you process more epochs, so multiple times the data set, and in terms of training time. So this shows it's comparable to the complexity of sequentially squares is comparable to the one of extended Kalman filtering. You can also extend the method to handle non-smooth and non-convex regularization terms even. So let's consider now an additional loss on the vector of parameters theta x, theta y in the problem. So this could be, for example, L1 regularizations, or even non-convex regularization terms like L0 regularization, or constraints that you want to impose on the coefficients, and then use ADMM iterations to compute a solution to the original problem, I've called these algorithm nails for non-convex ADMM iterations and sequential least squares. So the idea is that the ADMM update for the vector of original variables x0, theta x, theta y contains the extra quadratic term due to the ADMM iterations. This can be solved by sequential least squares, as we've seen before. Then the update of the new variables is the standard proximal step on theta plus w, which is the vector of dual variables you have in the problem, and for the equality constraints you have introduced by making a copy of theta x and theta y. Okay, and then simply update the dual variables here. Of course, the G function must have an easy to evaluate proximal operator so that this method becomes efficient. And what you can see here is an example where I have used as a G function a group lasso regularization on the coefficients so that I try to reduce the model order. Okay, so penalize the entries of the network coefficients so that by group lasso in each group there is a vector, a collection of variables that relate to a particular state. So by penalizing these groups, you see as a function of the regularization parameter, you will get models that have a decreasing order. So if this is very large, you will get order 0, so you will have basically a fit with the constant. And for intermediate values of theta, as you can see here, for example, for tau about 2, 3, you get a model which has still pretty good normalized root mean square error and a lower order, for example, 2 or 3. And this is another application of the same approach where now the G function is a quantization function. So this is a non-convex loss. So the function is 0 if the coefficient theta I belongs to a set Q. For example, I've taken here multiples of 0.1 between minus 0.5 and 0.5. So minus 0.5, minus 0.4, and so on. Otherwise, it's plus infinity. So if you plug in this loss term in the ADMM iterations, you end up with a model that, of course, has a lower score in terms of normalized root mean square error. But this is much better than what you will get if you first train the model by sequential least squares, for example. So you well train the model and then quantize the coefficients. A much worse model you will get. So this is very beneficial in getting a model that in the end it is very simple. It has coefficients that only are multiple of 0.1, which could help, for example, the implementation of the model in a very simple processor. The method is not guaranteed to converge. Actually, what you do here, you can run multiple least squares here, but you can actually run just one least squares and then immediately go at the next ADMM steps. Let me now show how to use machine learning ideas to learn hybrid prediction models from data, and in particular, piecewise affine model. So what is a piecewise affine model? Is a model where the set of states and inputs gets partitioned into polyhedral cells, and then in each cell there is a different linear dynamics with an affine term. So in general, if it is a state space piecewise affine model, the vector where we define the partition is x state and u, the input, and what you want to predict is the next state and the output. Now, there have been many techniques proposed in the literature for piecewise affine regression. So to train such a piecewise affine model from data, I mentioned here a few approaches that have been proposed. And the problem is it's not easy because you have to learn the linear models and the partition, so and the matrices defining the partition at the same time, so to reproduce the system dynamics. And here, actually, any machine learning technique that provides piecewise affine functions can be used. For example, neural networks based on ReLU activation functions, decision trees, softmax regression techniques can be used, even k-nearest neighbor return piecewise affine models as an output. Now, here is a new method that I've developed recently, which is actually, it's a general method for piecewise affine regression and classification. So you can train both continuous outputs and states and binary outputs and states. In general, states and output that can assume a value within a finite set of possible values. So let's say the feature vector Z, which is the vector collecting states and inputs in case of a state space model, or the vector of past outputs and inputs in case of autoregressive models. So in general, this is a machine learning jargon. It's called the feature vector, the input vector to the model. And the target vector, VC, is the vector of numeric outputs. Okay, so outputs of the model that take numeric value, as well as categorical outputs. So other output signals that can take a value within a finite set. So these are our training data set. Now, what the algorithm that it's called PARC for piecewise affine regression and classification does, it's a combination of clustering and solving read regression for fitting numeric outputs and softmax regression for fitting categorical outputs. So it starts with, say you have clustered the data in subsets. So you will fit by read regression a linear affine model for continuous outputs and a discrete model to categorical output by softmax regression. Then you also fit a piecewise linear separation function on these clusters of data that you have created. Okay, by solving, again, you can do this by solving a softmax regression problem. Okay, so the function you want to find is actually given by the maximum of linear functions whose coefficients you want to learn from the given clusters so that you can separate the clusters more as much as possible. And after you do this, then you can look at the data set and reassign the data to clusters based on a criterion that consider both quality of fit of the output functions as well as how much you are violating the piecewise linear separation, the partition induced by the piecewise linear separation. And you can show that you can converge to a solution, actually in a finite number of iterations, which may not be the global solution, but it's a local minimum for the problem, for the regression and classification problem you have posed. And here is a simple example. So I generated data, 1,000 samples from a nonlinear function. And if you fix the number here, a key parameter is the number of models, the maximum number of linear models you want to admit, in this case 10. The algorithm will automatically generate a partition, in this case of 10 cells, where in each cell there is a different linear affine function. And as you can see, the function is reconstructed quite accurately. And you're free to download the code from my webpage. Here is the link. Now let's see how we can use this algorithm to learn a piecewise affine model for use in hybrid model predictive control. So this is a toy example I've constructed to consider a problem in which you have a moving mass this is actuated by an input signal which is it's categorical, so it can only assume values 0 or plus minus f bar. And the mass moves here with some friction, and there are two bumpers that are connected to springs and dampers to these two walls. And I'm assuming the spring and the viscous forces here are nonlinear, so the dynamics overall is nonlinear, and is also switch dynamics, because as the cart hits the bumper, then they move together, and while moving together, they will transfer heat. So the two states here are position and velocity, and the temperature of the cart. So here is a data set that I have collected by exciting the cart with a random force. And you want to distinguish between three levels of temperature. Say you have the level green, yellow, and red, depending on where is the temperature. So what is the range of temperature? Now, what is assumed here is that you don't know the range of temperature, you only know the color. So what is in the data set, it's only plus minus f bar, so the input force, and the color of the temperature, okay? And then you have the state vector, which is yk, y dot, tk, fk, and then the target vector, which is the next position and velocity, the next temperature, and the color, which is the categorical output of the model. So it's a simple problem, it's already actually nonlinear and switching. So I run PARC on this model with 5 regions, and what you get, this is an open loop simulation on new test data. As you can see, the output of the continuous time hybrid system and the output of the discrete time piecewise affine model that has been reconstructed, it is pretty much similar. It's not exactly the same, but it's similar enough that we can consider this as a good model for MPC design. So let's do the design. So let's take the model, the prediction model. Here, the cost function, what you want to track. You want to make the color yellow. So I assume yellow is 1, and the green is 0, and red is 2. So let's put a set point on 1, on yellow, with a penalty if you apply a non-zero force. Okay, the input is constrained within these 3 values, and then the prediction has to satisfy the piecewise affine model equations of the model that we have learned with the PARC algorithm. Now this you can cast as a mixed integer linear programming problem with some transformations, and you can solve it, for example, with Cplex. It takes about 0.15, 0.30 seconds to solve in Cplex. And here you see the closed loop plots. The controller is able to make the switching nonlinear system stay within the area corresponding to the yellow color. And these are the actuated forces. If this is too complex to implement, what you can do is to generate offline data. So run the controller for random values of the state vector, and record the corresponding optimal input that is decided by MPC. And in this case, I have generated 10,000 samples out of the control law by solving 10,000 MILP problems offline, and then fit a decision tree on this data, and you get an accuracy which is pretty good. So the accuracy here is 99.9%. Accuracy in terms of reconstructing the right value for F, the force to apply. Now evaluating this control law online requires much less time, in the order of the tenths of microseconds, and if you look at the closed loop trajectories, they are very similar to what is shown here for the exact case. So this is a form of approximate explicit hybrid MPC that is obtained completely from data starting from an input-output data set, fitting a piecewise affine model, and then designing the corresponding MPC controller based on that model, and then excite the controller offline with mixed integer programming to generate a data set, and then finally fit decision tree, which will be our final control law to apply to the system. The last part of this lecture is about using learning methods for calibrating in an optimal way the parameters of the MPC controller. So we have seen MPC depends on several parameters, for example, the weights or the constraints on input increments and the prediction horizon. Even the tolerances that you use in the solver can be treated as calibration parameters. So there are many parameters. Some are intuitive to calibrate. For example, you know that if you increase the weight on a certain output, the tracking will get better. However, if you have many of them, calibrating all of them in an optimal way may not be an easy task. So the question is whether we can auto-calibrate them. So to do this, you can define a performance index for closed loop, for the closed loop response. For example, you can look at the square tracking error as an index of tracking quality over a closed loop simulation of the controller. And this would be a function of X, the tuning parameters that you have in the control law. So what is an auto-tuning problem? Having defined this function is the problem of minimizing this function with respect to the value of the tuning parameters. And you can look at this as a nonlinear optimization problem that you want to solve, you would like to solve globally. And there are many ways of doing this. First of all, you don't want to use you may use derivative, but you will have to differentiate the closed loop response with respect to the parameters, which could be very involved. And in particular, if the closed loop performance is measured experimentally doing derivatives, it's almost impossible. So we would like to use derivative-free methods, so black box global optimization. And there are many ways of solving global optimization problems without derivatives. And I recently proposed a new method, it's called GLIS, for global optimization using inverse distance weighting and radial basis functions. So pros and cons about auto-tuning. Pros, as we've seen, is that we have an automatic, fully automatic selection of the MPC calibration parameters, and you can apply it to the controller parameters, but also to the estimator parameters and any other parameters that appear and affects the closed loop performance. And the performance index can be rather arbitrary, since it's a black box optimization problem we are solving, so the function can be arbitrarily complex. Now, this is a pro, but it's also a con because you need to quantify the objective function. So you need to define a value for each given combination of parameters. And this sometimes is not easy to do because you may have multiple objectives in mind, and it's not clear how to blend them a priori. For example, you may have an average, a weighted sum of different objectives, but what the weight should be is not clear. And different people may have different ideas on how to assign a value to an experiment. And there is no room for qualitative assessment of the experiment. So if you look at two closed loop results, you say, okay, this looks nicer than this one, but quantifying this in objective function may not be easy. So for this reason, we have developed an active preference learning algorithm to try and minimize a function without measuring the function, but only based on preferences that a certain human operator expresses. So the idea is the following. The idea is that the function we are minimizing is hidden. We don't know the function. What we know is the preference between two values of the function. So when we generate two samples of the MPC parameters, in this case x1 and x2, we can ask somebody, can you please tell me whether you prefer x1 to x2? In this case, the preference is labeled as -1, or vice versa, if x2 is better than x1, then we assign a preference value of 1, or they are more or less the same, and then we consider this as a 0. So basically, we query the preference function pi by asking, in this case, the calibrator, which hides an underlying function that the calibrator has in mind, but is not quantified numerically. And what we want to solve then, finding the minimum of the function, means find a vector that wins all the preferences. Okay, so the optimizer will always be smaller or equal to any other value. So you would like to find a vector which wins or is as good as any other vector. Okay, so the algorithm we have derived is based on learning a surrogate of the function f by processing the preference values, so by collecting preferences. And this has been used for preference-based calibration, or if you can call it semi-automatic tuning of MPC. I've described the approach in this paper here, where you run experiments, you ask the calibrator to judge whether the new design is better or worse or the same as the current best design that you have found so far. And then, using the new preference values, refine the estimation of the latent function f and optimize the surrogate function together with an exploration term, so to come up with a new guess for what the optimal combination of MPC parameters should be, which you then pose as a new query to the calibrator to make a new assessment, and so on. Okay, and this converges to not necessarily to the global minimum, but convert to a good point in general. Actually, it would converge to the global minimum if you can run an infinite number of queries. So in the paper, we have tested this to calibrate a simple lane keeping controller based on a kinematic model in X, Y, and Cartesian coordinates and orientation. The objectives that the calibrator has in mind is to avoid obstacles optimally, have a pleasant drive, and also have small CPU time. Now, these are not easy to quantify in a single objective function. So what we've done is to run the preference-based algorithm, optimization algorithm, to choose 5 parameters: sampling time, the prediction and control horizons, and the weights on the input increments, in this case steering angle and increments in velocity of the vehicle. So after running a few experiments where each time you ask to compare two different closed-loop results, after 50 experiments, so after asking 49 queries, then you end up with a design which has this selection of the parameters, and this is the best that you have achieved by asking this limited amount of comparison. It's actually a pretty good design. So we found this a very natural way to add calibrators to calibrate, rather than moving parameters more or less with rule of thumbs and good sense, especially for calibrators that are not well trained. It may not be easy to figure out what the value of the parameters of the MPC controller should be. So in this way, this is an approach to help the calibrator quickly figure out what the optimal selection of the parameters should be. And we have extended the approach in this other paper to also handle unknown constraints. So when you calibrate parameters, there are some combinations which are infeasible. For example, when the closed loop gets unstable, that means that that selection of the parameters is not viable. It doesn't satisfy the constraint of bringing closed loop system which is stable. So you cannot even quantify a performance index in case of auto-tuning. So with this approach, basically we learn from failures, so from examples where the system gets unstable, that is not satisfying these unknown constraints we have underlying the calibration problem. And the algorithm will also learn the constraint function, so to figure out optimal solutions that are, of course, feasible. And this brings me to the conclusion of this lecture. I think I gave you the impression that learning-based MPC can be quite a good advanced control methodology, because it's quite a good combination of two powerful things. On one hand, MPC, which is a powerful control methodology for designing control systems, handling constraints, and dealing with multivariable systems, nonlinear dynamics, even switching dynamics. With machine learning, which is another powerful set of methodologies to, on one hand, derive models that you can use for prediction, and also to approximate the control law, or even getting the control law from data, for example, using reinforcement learning method that we haven't seen in this lecture. Now, ignoring the powerful tools that machine learning brings would be a mistake. I think I've studied myself a lot, different techniques in machine learning, and actually I learned a lot from this, so there is a lot of ideas there. So it would be a mistake not to look at these and try to see what of this word we can use for control design. On the other hand, we cannot think that machine learning can replace control engineering for different reasons. First of all, black box modeling, it's appealing, but in some cases it can be a total failure, because you're not able to capture the complexity of the dynamics just going black box without any physical insights. And sometimes you have to even adapt machine learning methods or develop completely new machine learning methods so that they are good for getting prediction models for MPC. For example, machine learning, typically people tend to deal with large-scale learning problem with a lot of parameters to learn, and the model structure is not very rich, so generalization to test data is a concern, and so there is not much emphasis on fitting the training data, but rather trying to get models that well generalize on new data. In training prediction models, what you want to get actually, since you have a lot of data for usually small models, the risk of overfitting is less critical, and then instead you want to get the best models you can get out of the rich set of experiments that you have collected. Also, designing an MPC controller and then approximate the control law completely offline, say fitting a neural network, can work well in some cases, but can be a failure in other cases. So when the problem is particularly difficult, then keeping online optimization for implementation is actually a good idea. So we shouldn't abandon the good tools for online optimization that we know. And reinforcement learning also can be not very good. So pure AI-based reinforcement learning applied to control problems, sometimes it works, sometimes it doesn't work. So to really conclude, this combination of MPC with machine learning really opens up a wide spectrum of opportunities for both research and applications. And thank you very much for your attention and for watching this lecture.